I'd like to introduce Aaron Aytok, who will be presenting an Internet Interconnection and Observability walkthrough. Aaron is no stranger to NANOG. When Aaron isn't volunteering his time with the program and hackathon committees, Aaron is currently a senior network engineer at CoreWeave. He's traveled here from Chicago to present today. Aaron has been up on stage here before, giving some updates on the hackathon. He's presented a BGP tutorial when we were remote during COVID, but this is the first time that he's actually live on stage here presenting his own content. So, welcome.
Thanks, everyone. Okay, I can see it on this screen. So yeah, I'm going to do my best to give a walkthrough of Internet Interconnection and Observability to all of you. This presentation is meant to be a high-gloss attempt to educate newcomers about Internet Interconnection and Observability. I'm a network engineer. I've spent most of my career focused on content distribution networks and Internet backbone architecture. Previously, for about 8 years, I was at Akamai. Currently, I'm focused on GPU and AI data center networks at CoreWeave. So I'm going to go from the ground up here. Some of this may be remedial for a lot of you in the room. Like I said, this is a talk meant for newcomers. So first and foremost, bits. If you didn't know already, computers digitally convert messages into zeros and ones. Off, on, in terms of electrical signals, is just simple. Those zeros and ones, we call them bits. A bit is short for a binary digit, and it follows the metric system. So 1,000 bits equals a kilobit, 1,000 kilobits equals a megabit, and so on. And network bandwidth is usually measured in bits. Bytes are usually reserved for storage. Routers. Routers forward bits by sharing and following routes of other routers and predefined standards and configurations that they're defined by. Networks interconnect their routers over physical cable or wirelessly over antenna to exchange bits and routes. And to transmit and receive bits over cable or antenna, bits are modulated into either electrical signals or light waves. So how exactly does that work? We refer to this as modulation or modulating bits, in particular on this slide, into light waves. Most industrial routers have empty sockets to plug in small modules, referred to as SFPs, small form factor pluggables. And these are transceivers, otherwise known as optics. Optics are rated to go different distances, specifically in kilometers, and speeds in terms of bits per second. So the latest Ethernet standard optics can reach 800 gigabits per second over about 1,000 kilometers or 620 miles. These are called 800 gig ZR plus optics. When you see optics, usually they are hyphenated with a reference of reach at the end of them besides their bits per second. So SR, DR, FR, LR, etc. refers to the max reach rated for the optic. Light waves have parameters that we can modify to encode bits or otherwise modulate. Examples of this are like modifying power. This is in particular amplitude modulation. And some examples of that are like if you can imagine a laser or a flashlight that effectively is beaming down a hallway, it can be off, have a weak, moderate, or strong intensity in its power. Wavelength or frequency is an example of modifying the color. So by changing the length of the wave, you're changing the color. And also by changing the wavelength, you're also modifying the frequency. So nowadays, in particular, when we refer to wavelength modulation, most of the time, we're actually referring to frequency in terms of specifying it on devices in terms of distinction. And then last but not least, phase, which is modifying the alignment or the offset of the wave to a reference wave. So some examples of modulation. The oldest way that I have here as an example is non-return to zero. So the idea of like when we are transmitting light, simply off or on is a way of transmitting bits, 1 bit at a time. A newer way is pulse amplitude modulation, or PAM, where we can send 2 bits at once, effectively faster, and it uses 4 distinct amplitude strengths, such as off, weak, moderate, or strong. And those are some examples of encoding bits as 00, 01, 10, and 11, depending on those amplitude levels or intensity effectively of the light. And then a newest way in terms of an example is quadrature amplitude modulation, or QAM. This combines amplitude, effectively the intensity of the light, along with phase, or the alignment or offset of the wave, to a reference wave. And with 16 QAM, we can send 4 bits at once with 16 different combinations. Those are some examples there on the slide. And with 4K QAM, we can send 12 bits at once with 4,096 combinations. 4K QAM is used in Wi-Fi 7, and I believe the latest standard of DOCSIS. Multiplexing. So to further increase efficiency, multiplexers merge and split, or mux and demux, different channels of colors or frequency over the same strand. This is referred to as wavelength division multiplexing. When we take many waves and densely multiplex them over strands of fiber, we refer to this as dense wavelength division multiplexing. Finally, another version of multiplexing is polarization division multiplexing, which is used to send different waves in different vertical and horizontal orientations. So if you were to imagine a simple graph of an axis going up and down and left and right, you can effectively send one signal here and another signal here and multiplex these signals down a single strand of fiber. Here are some visualizations of wave division multiplexing. So each laser sends a unique color or frequency, and thereby each wavelength is a distinct channel or lane of communication. When you're diagnosing light loss levels, and you're trying to read off the EEPROM of an optic, you'll usually see these references to channels, and in particular the amount of loss in dBm, or lanes, therefore, from these optics. And prisms and chemically tuned mirrors are used to mux and demux. So if you're familiar with the Dark Side of the Moon album from Pink Floyd, it's a perfect example, and as I have here on the slide, where by a prism we're able to send multiple different colors into the prism, and out comes a single stream that goes across the optical fiber, and on the opposite end effectively goes through another prism to split them back out. On the right was the best image that I could find under Creative Commons license, showing a Z-block, which are used in newer age optics effectively to use chemically tuned mirrors and stacking these colors of light together out into a single beam. Polarization division multiplexing, as I mentioned before, is used to send waves in different vertical or horizontal orientations. Coherent optics, which you'll usually hear more and more so nowadays, use DSPs, or digital signal processor chips, inside the optics to untwist these waves on each end. Before I go any further, I just want to say that this talk is not sponsored by any vendor, but as an example of talking about wavelengths multiplexing, I found a map from Zayo's terrestrial network here in North America, where you can effectively rent a color from them or lease a wave. You'll usually hear about around the NANOG circuit, people asking for, like, hey, can you provide me a 400 gig wave from A endpoint to Z endpoint? And here's just an example of Zayo's map of the routes that they provide where you can lease a wavelength or a color. Here is the telegeography submarine cable map from 2025. Mostly, again, the same, where instead of terrestrially, now we're going subsea. I wanted to specifically highlight this map as I see a common misnomer in society when we're talking about internet communication. Most of it is done by satellite. Traditionally and truthfully, most of this is done through optical fiber that's laid either terrestrially or going subsea. So case in point, most of the communication that you're doing between the United States and Europe, or the North America and South America, any kind of cross-continent communication, it's most likely going through submarine cables. Some examples of physical faults of these cables. Trench lines get accidentally cut by construction. Poles fall due to car collisions and weather, which is in particular very important for a lot of people here to get KMZs or files that they can load into Google Earth and see effectively fiber routes, and depending on their desires of diversity, seeing if these fiber routes from different providers go along the same side of the street, along the same pole, and are effectively vulnerable to the same kind of faults, such as a car collision, if not a weather taking out the pole as an example. Sometimes these poles catch fire, and I didn't explicitly reference it on this slide, but those fires can be caused by, unintended electrical failures. They can also be sabotaged. Ships, anchors drop and cut subsea cables, usually close to port, but they can also happen well outside in the middle of the oceans. Signal is prone to decay by dust or weather. Transceivers, inline amplifiers, and routers go faulty. Electricity or cooling fails. Humans make mistakes, etc. Where the light meets business. Facilities is a common term that you'll hear around the NANOG circuit. Facilities refer to data centers, and as well, carrier hotels, universities, utility, and water closets. If you're familiar with that last term, yes, I do mean that. So in particular, this hotel that we're staying in, like many, can be effectively a carrier hotel. In the basement, they provide interconnection to different networks, and effectively is a point of presence for them to interconnect. Facilities rent you different things. An example of this is space, like racks or cages. Cooling, hot and cold aisles are usually diverse in terms of when you're ordering hardware for said data centers, you need to know if you're ordering your router to have front to back or back to front airflow in order to align appropriately with these hot or cold aisles to bring in cold air and exhaust out hot. You can also rent power effectively from these facilities, such as a kilowatt, the amount of kilowatts per rack, and as well distinct feeds for redundancy in these racks. And as well interconnection, which I'm realizing is a very hard word to pronounce. Cross connects are otherwise referred to as XCons. These can go rack to rack, cage to cage, or rack cage to an MMR. An MMR is a meet-me room, which is effectively just a centralized place that the data center has designated for everybody to interconnect at. Something that I've left off the slide here, which is pretty obvious though, is that data centers themselves can have campuses where effectively you're connecting in between these different campuses of the same company. If not, you're going across cities, potentially even countries in terms of site to site. Now, usually, effectively, the facilities are not laying their own fiber where they are providing these like distinct site to site connectivities. They are networks within those facilities that are providing that. And thus, by you connecting to the facilities that these networks are in, they can connect you to different cities or different campuses or data centers. Facilities are not meant to remain empty. Usually they have a lifespan of anywhere from 7 to 15 years in terms of the purpose that they were built for, or in particular the specs or plans in terms of the customers that they expect for the longevity of time. Sourcers find facilities with resources for the best price. So commonly in this industry, you'll refer to people specifically in sourcing. This is what that means. Some networks end up having to build their own facilities depending on their user needs. And as demand increases, resource supply in dense metros is becoming ever so much constrained, such that it is implied we'll have to continuously build further out from these dense metropolises into unprecedented communities. So more so and more so, as time goes on, it's not about necessarily having facilities in Chicago or San Francisco or Dallas, Texas, but more unprecedented communities further out from these metropolises. Usually, networks will have different intents of when they are building out to possibly even interconnect up back to like these dense metropolises. So as in, like, if you're going to go build in the middle of nowhere, you still need to interconnect usually into dense metropolises and have fiber routes that provide that. You'll often hear about the buying and selling of waves or dark fiber. Waves we touched on a little bit earlier, which is quite literally just leasing a color off of a strand that gets muxed and demuxed on each end. Effectively, that's your color, and you get to use it for your transmission exclusively. Or dark fiber implies that the link is not yet lit, and you are expected to light the strand and mux or demux wavelengths or frequencies as needed. Besides leased waves or dark fiber routes for site-to-site connectivity, networks connect to each other with different business relationships locally in these facilities. Ultimately, waves, fiber, and interconnection in these facilities is what makes up the internet of today. But how do you participate? First, you have to register. And by register, ultimately, you need to register for numbers and pay for those numbers. 5 regional internet registries, or RIRs, assign numbers to distinguished networks, machines, and their purposes. They are ARIN, LACNIC, RIPE, AFRINIC, and APNIC. There are as well independent brokers that resale and auction numbers. So when you go to an example of an RIR like ARIN, you would need an autonomous system number to get started as having your own autonomous network, which will be provided a number, and this provides network identification and distinction. You'll also need internet addresses or internet protocol addresses, aka IPs, to distinguish machines, and they are usually aggregated into larger blocks. We generally refer to these blocks as prefixes. Out of RIR region use of these internet addresses and ASNs is sometimes permitted with conditions. So for example, if you were to try and lease space from one of these RIRs that is designated for a region, and in particular by space, I mean IP space, if not an ASN itself, it's usually asked that, like in the example of unicast services, that you would at least route the majority, or if not the block that you are leasing in that region itself. And if you want to use it elsewhere, they usually are permitted with conditions. There are some exclusions to that I'm not going to get into. And in terms of any cast, the same kind of principle applies, where the intent is effectively for you to at least route it within the region that you are leasing the space from said RIR. And then you may have heard of this thing called IPv6. I'm not going to get into the weeds of IPv6, but in particular, IPv6 was an evolution of IPv4 that was mostly driven by resource exhaustion. So simply put, with IPv4, there's 2 to the 32 amount of addresses, and for IPv6, there's 2 to the 128. In theory, we'll never run out of IPv6 addresses. So BGP is how effectively autonomous system numbers and IPs come together. It's a standard implemented in software used to exchange routes to IPs within autonomous system networks. BGP is the routing protocol of the internet. BGP has evolved and extended its capabilities over time. In terms of its best path selection algorithm, in simplistic form, the most specific destination with the shortest path wins, in terms of having many paths available to you or next hops. And last but not least, BGP has many traffic engineering possibilities. BGP has business relationships implied, generally referred to around this circuit as peering. So within BGP peering, there are classifications of these business relationships that, again, I'm going to give a high gloss summary over. The most popular, I think, that you'll hear about is transits, comparable effectively as an analogy to you paying a courier like FedEx to deliver your package anywhere in the world. In theory, that's what transits are meant to be. They're supposed to get you to any destination. But as I'll get into a bit later, and as has been discussed at NANOG in the past, in practice, every network has a different view of the internet. There is no default uniform set that everyone is comparing against. So transit network capacity to other networks is also shared amongst all of its customers, and lossless delivery is not guaranteed. Further, in terms of how you effectively pay for these services or transit, is usually referred to as burstable billing, or 95.5. Transits sample how much you use over a month, and then they will sort those samples high to low. They ignore the top 5%, effectively bursts, and you are billed the next highest number for the month. In other words, brief spikes are free. Transit services can be resold, and this makes up a large amount of the internet service provider economy. Thereby, transit providers are tiered. So you'll often hear of tier ones. They are effectively at the top, and in theory, they should have no upstreams or transits above them that they are buying from. With that said, though, tiers can change by geographic market. While a network can be a tier one in one region, possibly in another that they are growing into, they are either temporarily or permanently buying transit from an incumbent. The other example of BGP peering business relationships is P&Is or SFIs. So P&I stands for Private Network Interconnect. SFI stands for Settlement Free Interconnect. This implies direct connection to another network that is usually at no cost. There is a mutual benefit seen, and thereby a reduction of costs that you're paying to transit, where instead of you're sending all of your bits to transit, now effectively you are sending a portion of those bits directly to a network that you do a good amount of traffic with. And in the idea of a P&I or an SFI, now you effectively have reduced your costs in delivering to this network. One of the two networks still has to initiate and pay the facility for the cross-connect. I left it off the slide, but another acronym you'll often hear about is an LOA, or a letter of authorization. This is effectively a short letter handed off to the data center saying that I authorize this other network to interconnect with me, and this is all intended. There's no malice here. Optics, IPs, and routers, ports have costs too. When you're effectively buying hardware from these vendors, every single port on that faceplate has a depreciation cost, and sometimes, depending on who you are and who you want to interconnect with, it can come with constraints. So besides like open peering policies and selective peering policies of who I actually allow to interconnect with me, there's also this notion of at what rate are we actually going to be, or what volume of traffic are we going to be exchanging? And based on the router that I have purchased and the ports that it can provide me to interconnect with different networks, if we only do a little bit of traffic with each other, I may not want to sacrifice a port that can do a lot of bits per second for a very small volume with another network. We'll get into that in a subsequent slide, which is here. In particular, IXPs, or Internet Exchange Points, otherwise abbreviated as IXs or Internet Exchanges. They are comparable to a potluck. You pay a renewing membership fee and then can exchange traffic with everyone in the room. So effectively, you'll pay a membership fee to the IX, you'll interconnect with this IX at a set speed, and then everybody else that is a part of that switching fabric you get to communicate with. And usually this can be reserved for lower volumes of traffic, where if you cannot necessarily qualify to directly have a P&I with another network, you can potentially meet them or interconnect with them at an IX, where it is meant to be a community service of sorts. Especially in unprecedented communities, IXs are kind of one of the ways that interconnection starts. So if there are no facilities in a common area, but all of a sudden there's growing network demand in said areas, possibly a community internet exchange could be started. IXs provide route servers for everyone to BGP peer with, and those route servers will effectively reflect those routes to all of its clients over BGP without having to directly peer with every single member. You can choose to use the route server, or you can selectively peer, or you can do both. Effectively, you can do both simultaneously. There are some networks nowadays, I won't get into the specifics, that are not as willing to peer with route servers anymore. And while they will interconnect with IXs, they want to directly choose who they are peering with, who they are exchanging routes with, and they effectively have more granular control over those relationships, thereby having explicit peering relationships. So in summary, transits are a middleman network. They have distant routes, and you pay the highest renewable cost. They're often referred to as upstreams. A little bit more context there. While transits can have distant routes in terms of long reach delivery for whatever kind of traffic destinations that you have, they also as well have local routes. But the point is that when you're connecting to a transit, the idea is that this is effectively a relationship where you do not already have a more direct one with any set network, and thereby can be implied that it possibly is going to require many hops and potentially geographic distance to reach certain destinations. Now, as with a PNI or an SFI, you have the most control over your capacity. The cross-connect is effectively the only third-party and cost. So in other words, the data center that can provide you this cross-connect can effectively be vulnerable to faults as well in terms of a third party and charge you a cost. And then lastly, internet exchanges or IXPs. It's a middleman network. You're vulnerable to any faults of the switching fabric of the IX, and you generally pay some renewable costs. A middleman network implies, in short, additional risk of loss. So in terms of how we determine how exactly we establish these peering relationships is by sampling traffic. And the idea of sampling traffic, every n number of packets ingressed on a link will have attributes like a source and destination address that is copied to a collector for analysis. And in this analysis of network flow, aka net flow or flow for sources and destinations, you can see effectively who are your top talkers, or top sources, top destinations. And when you're first starting your own network, effectively if you just get a transit interconnection and sample from that point, you can determine possibly from that point forward who you want to directly peer with over a PNI or an IX to reduce your transit costs, increase performance, have more control over your capacity, and any other issues that may arise. Flow in particular as well helps in diagnosing issues with routing and attacks, and you can even use flow to filter and mitigate the impact of attacks. As I kind of got ahead of myself there, this slide talks about top sources and destination ASNs by flow sampled. Some more questions that you can effectively ask with that analysis are how much are you paying for those bits via transit, and whether or not you can get a peering relationship that is near settlement free to reduce those costs. Is the considered network in the same facility or the same IX as you? If not, how much would it cost to reach? And then how much are cross connects, optics, IPs, and possibly even membership fees for internet exchanges and their reoccurring costs? What is the network's peering policy? I briefly touched on this before in terms of open versus selective. Some networks, if you go onto peeringdb.com, which I'll get into a little bit later in my slide deck, will designate whether or not they have an open or selective peering policy. Open implying that as long as we have some communication in terms of establishing peering, you can come and peer with me. Selective implying that we are a bit more granular in terms of our selection of who we peer with. And usually this is related to how much capacity you are trying to interconnect with. As I touched on previously, depending on how you value your ports on your faceplate and the volume of traffic that you're doing with a certain network, it may not be cost effective for somebody that you do a very low volume of traffic with to sacrifice an entire high-speed port. BGP paths and views are unidirectional, and asymmetry of traffic flow is common. So in other words, while the path that I take to a certain destination is not guaranteed to be the same path back. Redundancy does not imply true diversity. I gave examples of this previously, of the idea of if we're all having fiber strands go over the same telephone pole on the same side of the street, something happens with that pole, effectively we're all taken out. So even though I have possibly interconnection with different fiber providers, we need to ensure by looking at their KMZs in Google Earth or possibly other softwares that can determine if there is true diversity of these routes. And then, last but not least, transits as well. If you go and purchase transits from different providers, but they have the same upstreams, you don't necessarily actually have diversity in your service. Today, internet traffic and demand is strongly centralized to a common set of destination networks. Some of us often are concerned about what about the rest. So while most of our users or eyeballs are reaching destinations like Google, Facebook, Netflix, etc., there are many other destinations of the internet that we are responsible ensuring we can provide delivery or connectivity for. And there is no global uniform internet or set of routes that everyone is trying to effectively match or have. And research done by Jeff Houston that I reference in this talk, he gave this talk in 2016, and I think during COVID we also did it remotely as a spotlight, talking about desperately seeking default, which he goes into the research of showing that there's a significant standard deviation comparing different network views of the route sets that they have and effectively the address reachability. I highly recommend you check out that talk. Also, Per Sider Report, which is a project of Jeff's, has different internet statistics that I'll also jump into a bit later that shows that about 60% of networks are only seen via one path. So network engineers need to strategically announce and filter BGP path views to best serve their customers. As I touched on before, some views can contain geographically distant but short AS paths. So while I may interconnect to a transit network and they can provide me different routes of certain destinations, these AS paths may be very short, but they actually go long geographical distances. Views may also contain lossy paths due to congestion or faults. Views may contain tromboning or looped paths. Tromboning implying the idea of if I'm trying to reach a destination in Los Angeles, but my traffic has to go all the way to Chile and back, this is a tromboned pattern of traffic effectively going a scenic route unnecessarily. Or looped paths in the idea of maybe my traffic never reaches said destination due to some sort of misconfiguration, and ultimately my packet just keeps circling until effectively TTL expires and it just gets dropped. Lastly, views may contain adversarial paths that network engineers actively try to mitigate. So an example of advertising BGP paths in different manners, selective announcement is strategically manipulating the reachability of your announcements. So selective announcement can in particular say that I want to announce my IP address to said provider, but maybe not another. It can also be based on the prefix length or the specificity of the destination. You can advertise more specific prefixes to attract traffic as a tactic. There's also AS path prepending, where you can extend the path of your destinations artificially to dissuade traffic. And lastly, communities, otherwise tags. You can attach signal to trigger actions by peers. Some are defined by the IATF and are effectively referred to as well-known communities. Some examples of this are black hole, where you can add a tag to your destination and say, hey, I don't want you sending me any traffic for this destination. If you receive any, effectively discard it. Graceful shutdown is implicating that I'm about to undergo some form of maintenance. Please depreference my routes, take a different path. I'm about to go away in set amount of minutes and intending to shift this traffic gracefully before I do so. No export is the last example that I provide here for well-known communities, and no export implies that when I advertise you a destination, I don't want you advertising it to any other network. Some communities are provided by networks themselves that are unique to them, where you can use them on your own prefixes that you advertise to these networks. And an example of what these tags can do is, besides no export, selectively advertise or not advertise prefixes to other peers of the network that you are interconnecting with. And then on the opposite direction, receiving BGP paths, we can filter against explicit prefix lists and or attributes such as their path length or communities that they come with. You can validate the route origin ASN and path. This is referring to RPKI ROA and ASPA. ROA standing for Route Origin Authorization, and ASPA standing for, I'm calling myself out here, Autonomous System Provider Authorization, thank you. And then verify source address is in the table or matches an ingress interface as URPF, unicast reverse path forwarding. In particular, RPKI ROA has been around for a minute now. It is not entirely fully adopted. I'll get into that in a future slide. ASPA is very new to the industry and is only recently getting implemented in RIRs and hopefully soon different network operating systems to use against route path authorizations in terms of designating who are your upstreams. So the intent of this, besides route origin authorization, saying that only certain ASNs are authorized to originate said prefixes, we also want to specify who's authorized to be our upstreams and effectively mitigate route leaks and other tactics of jeopardizing AS path reachability. So I'll get into this in subsequent slides. BGP paths can be hijacked for either man-in-the-middle or denial of service attacks. Here's an example of a picture that I found from phoenixnap.com that talks about how the intended destination of AS65005 trying to reach this destination of 1/8 is advertising 1/8. You have some sort of network that interconnects with AS65005, but it also interconnects with 65002, or at least receives paths from these networks. And AS65002 is not the authorized origin of this destination. And even further, they are advertising a more specific path. So the intent of this is to capture the traffic either accidentally, maliciously, or for adversarial purposes. And RPKI ROA is meant to mitigate said circumstance, where by publishing in the RIRs and RPKI ROA, you can specify that only 65005 is authorized to announce this prefix up to a max length. So here I go into that in a bit more detail. Besides actually signing ROAs in RIRs, you also have to have your routers validate if those paths are RPKI valid, invalid, or unknown. So the 5 RIRs act as the root trust anchors, otherwise known as certificate authorities in different industries for like SSL certs or TLS certs. ROA records sign a prefix's origin ASN and max length, as I touched on earlier, and ASPA records sign an ASN's upstream providers. Manners is mutually agreed norms for routing security. Abbreviated as manners, it is meant to imply good manners of internet practice, and they ask you to adhere to these 4 norms: filtering to prevent propagation of incorrect routing information, anti-spoofing to prevent traffic with spoofed source IPs, coordination to maintain globally accessible contact info, and global validation to facilitate validation of routing info. So getting into observability. I'm going to go into different sections or forms of observability. Some of these, again, are high gloss summaries of what these services provide and that I'm targeting in this presentation. They are not to say that these are the only things that these services provide. But in the example of databases, RIRs as well provide IRRs, or Internet Routing Registries, that can determine who is who and what are they attesting to route. PeeringDB is a database that can tell you what facilities networks are in, the metadata of set networks, and contacts potentially to reach those networks for certain reasons. RIPEstat, provided by RIPE, is a multi-tool for historical analysis and resource lookups. And CADA's ASRank and QRadar's Radar can provide BGP relationships, network cone sizes, events, etc. RPKI observability, NIST provides an RPKI monitor and as well Cloudflare as examples. I'm sure there are others. They provide global adoption statistics in a dashboard format and an interactive explorer to browse global ROAs and BGP announcements. And Cloudflare also provides this website called bgpsafeyet.com to test to check if your ISP is dropping RPKI invalid routes. Route archives and observability. Some of the most popular ones are referred to as, on this slide, route views and RIPE-RIS. Both of these projects have been going on for multiple decades to collect and archive routing data. You effectively peer with route views or RIPE-RIS. They will collect those routes and archive them over a time series, and researchers and otherwise network operators can reference this data for diagnostics and analytics. RIPE also provides this service called BG Play or BGP Play to visualize BGP route propagation and timing. Cloudflare also has a service referred to as Cloudflare's Radar that shows internet trends and anomalies. Georgia Tech also provides some services that I appreciate, one of them being GRIP to analyze BGP hijacks, and Georgia Tech's IOTA to observe internet outages. There are some others here as well. BGProutes.io aggregates all those different routing route collection services such as route views or RIPE-RIS, some others as well like Packet Clearinghouse and CGTF, and aggregating them all in a centralized place via a web tool, if not an API as well, that you can use to do analytics on this data in an aggregate form. Jeff Houston also runs bgp.potaroo.net and ciderreport.org that provides a variety of research stats and graphs. BGP.tools is as well a network metadata aggregator and route collector, provides many services comparable to others as well. I wasn't quite sure exactly where to fit BGP.tools into this slide deck, but I wanted to cite it. And then kentic.com/blog also does some analysis of large-scale BGP events, in particular Doug. So Doug Mattery publishes on Kentic's blog his analysis of different large-scale BGP events, such as hijacks, leaks, and blackouts. When it comes to measurements, RIPE Atlas is a global network of distributed probes for active measurements. RIPE Atlas's interface can be challenging for some. GlobalTraceRoute.com is a friendly front end for RIPE Atlas, where you can effectively select RIPE Atlas probes and issue single measurements to certain destinations. NLNOG Ring is a community of networks providing shell access to internal servers for debugging, also communities. And then Waveform provides this buffer bloat test to measure effectively a speed test and latency under load. Lastly, in terms of summary, and then we'll get into a bit more specifics, reputation and location sources for observability. Here are some examples. On the left, in particular, being reputation focused, and on the right, location focused. These are, again, this talk is not sponsored by any of these companies on this slide or institutions, organizations. They're just meant to provide examples. So on the left, Akamai being an example of a CDN service that is well known and used across the internet today. They effectively provide a client reputation service that I'll give an example for soon. Effectively, when you're trying to reach Akamai destinations based on the reputation of your source IP, you may or may not be blocked. Proofpoint, email service provider for filtering, and effectively does the same thing in terms of reputation based on IPs. Spamhaus, Team Cumry as well. And lastly, Spur. Spur in particular is focused on reputation of IPs for residential proxy services, which is unfortunately a growing threat to the internet landscape, where malware is effectively placed on certain hosts that are then resold to masquerade nefarious or adversarial traffic, and is meant to be perceived as actually coming from a residential source or like a end user in some suburban neighborhood. Spur is in particular trying to analyze effectively residential proxy services and build reputation based on source IPs of if they have residential proxy services being based off said IPs. On the right, geofeeds is a popular topic. It was talked about on the stage yesterday in 2 different talks. Some of these references were also mentioned in those talks. Geolocatemuch.com is an aggregator of a website, a web tool that you can visit to effectively see all the different IP location providers, and as well how effectively they interpret geofeeds, at what frequency, how often effectively they update their data. As well, based on the same founder of geolocatemuch.com, there's a GitHub tool or a GitHub repo that you can fetch, GeoFeed Finder, that can effectively go and pull geofeeds from the RIRs and aggregate all that information together for you. I noticed I kind of skimmed over this. In particular, geofeeds, as a quick highlight, is a way for networks to specify the location of their addresses. And then lastly, there are services effectively that are doing this as a third party to analyze the location of these IPs. An example of one is MaxMind. It's not meant to exclusively say that MaxMind is the only one. So let's explore some of these observability tools that I've cited. I tried my best to find a network that was close to San Francisco for example's sake. UC Davis is nearby. So who is networks.cs.ucdavis.edu? We can do a simple DNS query and see that it has this IP address, 169.237.5.191. And then we can ask Team Cymru via their whois service, who is this IP address? They can refer to the ASN that the IP is routed out of, the specific BGP prefix that's being routed for, or the most specific BGP prefix for that destination, the registry effectively that it is allocated from, and when it was allocated in 1995. Lastly, an AS name of, in simple terms, who is this network? Explicitly there, University of California, Davis. You can look up University of California at Davis on peeringdb.com. Their page doesn't really have a lot of information, but you can see their ASN there. This was meant to show an example of what peeringdb.com looks like. PeeringDB also provides an API service, but just as a visual, you can see the different metadata that can be included for a network, such as a route server or looking glass address, the amount of IPv4 or IPv6 prefixes that they're intending to route, and thereby you can set max prefix limits to mitigate any kind of unexpected announcement of a large volume of prefixes that are unintended, as well as their traffic levels, whether they're mostly inbound or outbound heavy, etc. And on the right, you can potentially see for different networks, the University of California at Davis doesn't have anything published on PeeringDB, but if they have any points of presence for public peering, if not direct interconnection, they could list them there. So CADA also provides this AS rank service. I also recently heard yesterday that sales teams, which I think we can infer are from these different transit networks, often actually looking at CADA's AS rank as like a very determining factor of where they are in the market for how many customers they have. But as a network operator or network engineer, the main way that I use AS rank or inspect their data set is to understand different peering relationships to determine if routing announcements are happening as I desire. So we can see UC Davis has 4 transit providers. Relationships in AS rank are categorized as provider, peer, or customer. So provider implying transit, peer implying a direct peering relationship, settlement free, hopefully, and then otherwise customer being somebody that you resell your services to, in particular transit services. They can also be internal ASNs of your network that are effectively using a different ASN of your own as an upstream. But the point of this slide is to show that UC Davis, per CADA's AS rank, has 4 providers. Those being AT&T, 7018, Scenic from 2 different ASNs, 2152 and 2153, and lastly Comcast at 33667. I wrote a very simple bash tool that can use GraphQL, or in particular CADA's AS rank GraphQL, to query this in a CLI format. So I can just type ASN-rel 6192, and it can just return to me effectively the relationships. So here's an example of that, and effectively just in CLI format, the same data. BGPQ4 is intended to be a tool to build prefix lists. So if I was to peer with 6192 and I wanted to establish a prefix list for this provider of attesting who or what they are expected to route in terms of prefix destinations, you can see those here. I've also done a little string manipulation to just filter out the config that usually comes from BGP-Q4 to like put onto a Cisco router. That's already like predetermined configuration. You can just copy paste. But the point of this is that BGP-Q4 can also be used in like a lookup manner to understand what 6192 is intending to announce. Further, BGP-Q4 has this enhancement in it as an evolution from BGP-Q3, where if a network doesn't necessarily have a route object published in an RIR IRR, if they have an RPKI ROA attesting for a destination to their origin ASN, BGP-Q4 can also find this and include it in the prefix list output. And then RIPE-RIS as well has an API that you can query effectively of all their different route collectors and see the different prefixes and paths for this destination. And so this quick bash tool that I wrote can just aggregate that information. And this is not all of the output. It is just a subset that I highlighted to show effectively the destination prefix, the amount of peers that are seen for this path, the upstream in particular from the origin ASN, and the AS path length for however many peers are seeing that path, and as well the amount of prepends that are being done by the origin ASN to either artificially or not artificially extend the path length. So by this output, the intent is to see that for this destination, effectively 7018 is its primary upstream, as it's not prepending the 7018 paths, whereas the other paths they are prepending that I just didn't include in this output. Here is effectively a different output of the same data set of still querying RIPE's route collectors, and instead of aggregating it as I did in the previous slide, a bit more verbose here of seeing the different AS paths and communities that are attached to those paths. RIPE Atlas is in particular a service to use probes provided by RIPE that are running in different networks to run measurements effectively to different destinations. And on the right is Global Traceroute, which is effectively a front end for RIPE Atlas, where you can select RIPE Atlas probes and issue measurement to specific target destinations. And on the left, you can see a map of all the different RIPE Atlas probes that are distributed in different networks. On the right, you can see in particular this probe trying to reach this target address and a trace route effectively for that. And so this target address is the cs.networks.ucdavis.edu. And so from scenic, effectively trying to reach this target address, this is what the trace looks like. You can also see at the bottom there the source address of the probe as well. Here's an example of bgproutes.io looking up the same destination, where instead of just querying RIPE-RIS, you can effectively query, I don't know how well you can see it on the right there, but the different collection sources of different route collection services like route views, PCH, CGTF. Yeah, so it's a centralized place. Instead of querying each route collection service independently, you can just use bgproutes.io to query all at once. And this is a hopefully better seen screenshot of specifically this destination seen by bgproutes.io from all of its different vantage points. Only has a 52% visibility. So the point being, as I referred to in previous slides, is that not everyone has the same view of the internet, and in particular different destinations such as this one. On the bottom is a snapshot from RIPE-Stat, where RIPE has about 320 different 320 different vantage points effectively to see this route from, and it has 100% visibility from those 320 different vantage points. Whereas bgproutes.io, it can only see it from 52% of them, roughly. This is again meant to highlight that not everyone has the same view. Here's an example of RIPE's tool called BGPlay, where in the previous slide, actually quickly going back, they actually referenced the first ever seen announcement of this destination by 6192 happened fairly recently on January 23rd. And 8 UTC is actually when they archive, at least from what I observed. So it's not actually the exact moment that the route was announced, but when the archive was taken. In this short clip that I'm about to show from BGPlay is a visualization of the route being announced from 6192 for the first time. And so you can effectively see the announcements happening, going to different networks as the path propagates. And it's a pretty cool visualization. So recently, coincidentally enough, as I was building this talk, UC Davis apparently was experiencing some form of network degradation. It says here that on their status page, UC Davis was currently experiencing a degradation due to bandwidth constraints. The NOC is attempting to engineer traffic flows to balance the load across multiple ISPs to stabilize. Using Georgia Tech's IOTA service, we can actually observe this around the same timestamp. They are measuring internet connectivity to different destinations, and we can see a dip effectively in this internet connectivity around the same time. You can also see an uptick in round trip time latency to this network using the same IOTA service provided by Georgia Tech. And here's a more CLI output of the same information that we've kind of been observing via BGPlay and as well from RipeStat's output of when this archive was taken, specifically, where you can use a tool called BGP dump to analyze these MRT files that are effectively the archived aggregate set of when they selected to archive their data set of views. And you can search through or grep through these views for a specific destination. So just reading this quickly through, a table dump taken on January 23rd at 8 UTC sees from these different networks, such as like 34549, 37721, 58057, this destination and the BGP path that they are effectively sharing with RipeRiz. Cloudflare also provides their radar service that I touched on before. We can see around the same time that there was an uptick in BGP updates from this network. And as well traffic trends. Something that's really interesting when we look at these traffic trends provided by Cloudflare's radar, you can effectively see on the left side of the graph a low volume of traffic. Effectively, students are still on summer break, and we can see when they come back, and then we can see as well when they go on effectively Thanksgiving break and come back, and then lastly on their winter holiday break at the end of December, and then come back in the first or second week of January. So it's a really interesting pattern that you can observe via Cloudflare's radar of different traffic trends of networks and almost build a story, if you will, of what happened. On the left and right here are pictures of graphs from CIDR report showing active BGP entries of IPv4 on the left and IPv6 on the right. So on the left, effectively 1.1, roughly 1.1 million IPv4 addresses are seen. And on the right, just about 250,000, 250,000 for IPv6. NIST provides an RPI observability platform to see and track effectively the amount of, at least in this screenshot, the amount of IPv4 space that has RPI ROAs that are valid, invalid, or not found, or otherwise referred to as unknown, as well as in the middle there, the count of the total amount of routes that they're observing. Not so recently, but not so long ago either, the amount of valid routes was able to exceed the amount of routes that were not found or had no RPI ROA published. And the amount of invalid routes at the bottom there, you can actually see a little bit of volatility in, but thankfully is relatively low. At least for this destination, looking it up in NIST RPI Monitor, you can see that there are no ROAs published for these destinations, and specifically the one that we've been looking for. So the University of California, Davis does not publish ROAs for their address space. This is another example that I can't quite remember of different networks and effectively as well as showing that they are, I think this is effectively being able to just specify different ASN and see whether or not they have ROAs published. As well, just a aggregate set of invalid prefix origin pairs that you can observe at a certain date, hour, from a certain RIR, and their designation of valid or if not valid, and protocol. This is Cloudflare's is bgpsafeyet.com. I have Comcast at home, so I can easily use this web tool, click test my ISP to see if, in particular, Comcast is implementing RPKI ROA validation. So to be clear, while you can publish ROAs for your address space, it is still upon other networks to validate against those ROAs or not. And so the intent of RPKI and publishing ROAs and as well ASPR records is to mitigate the chances of man-in-the-middle attacks or BGP hijacks either due to accidental or nefarious purposes. And is a twofold game in terms of it's not just about publishing the records, but whether or not the network that you're actually using is validating against those records or not. So in this case, we can see that Comcast is. Simply what Cloudflare does is they have two endpoints here, valid.rpki.isbgpsafeyet.com and invalid, that go to different destination IPs that are in different /24 prefix blocks that you can see whether or not are reachable by the network that you're behind. And the idea is that ideally the invalid destination is not reachable, that traffic would be discarded because as Cloudflare is intentionally routing that against its own RPKI ROA record, it is meant to be a test of validity if that network that you're using is implementing RPKI ROA validation. Here's an example of looking up those web addresses and effectively the IPs that they point to. And as you can see, they are in different IP networks. Here's an example of me looking up Comcast and PeeringDB specifically to use the route server to show you an example of how exactly a view, if you will, inside Comcast network to see that this route is effectively the invalid one not being seen or routed by Comcast, or sorry, being able to be routed to the destination by Comcast. So when looking up the former valid.isbgpsafeyet.com address, we can see that this /20 is in Comcast's table, whereas the invalid address is not. And so thereby effectively implementing RPKI ROA validation and discarding those destinations or not installing them into their tables. Scenic was another upstream of UC Davis, and so this is an example of their PeeringDB page, and as well the looking glass that they provide, which is on bgp.tools. So in other words, Scenic peers with bgp.tools, and then bgp.tools provides an endpoint for you to get a view into Scenic's network. And unfortunately, as we can look up the invalid destination, we can actually see it in Scenic's tables. Two different views thereby, one from Los Angeles and one from Sunnyvale. This thereby implying that Scenic is not doing RPKI ROA validation. As well, there is a RIPE Atlas probe within Scenic, and so beyond just looking at bgp.tools looking glass that is provided for Scenic, we can actually use this probe inside Scenic's network to see if this destination is reachable. And as you can see in the trace output there, we are actually able to reach that destination, thereby further confirming, unfortunately, that Scenic is not implementing RPKI ROA validation in their network. Here is the client reputation service that Akamai provides for endpoints. You actually have to be the client yourself to run this web tool and effectively determine if it has a bad or no reputation therefore. In this case, this is an address, I think, from DePaul University, and it did not receive a bad risk score according to Akamai, or otherwise, it does not have any bad reputation or known for any nefarious or malicious purposes. If for whatever reason you have IP space that is determined to previously have a bad reputation that you have now transferred to your own network to use for your own purposes, this is something that you might have to go through in terms of checking the reputation of your recently allocated blocks to determine their previous reputation and how to clean them up going forward. Last but not least, referencing this slide, it's a common experience for end users to not understand effectively why they're not able to reach certain content by networks. And often it can be that the network is using some form of CDN that does client reputation and wants to filter out by some manner malicious or nefarious traffic. And this is a way of auditing, at least by Akamai standards, the reputation of those source IPs. Here's an example of Proofpoint's web tool to look up the IP reputation. It doesn't really have much here to say. It was effectively me doing the same lookup at DePaul and seeing that this was not blocked, and otherwise Proofpoint doesn't have any bad reputation or risk score for this source address. Further as well, using Spur, it doesn't seem like there is any known residential proxy service or anything that Spur designates as a bad reputation score for this IP. Geolocate much, I touched on earlier. It was also touched on in a couple presentations yesterday. It effectively shows not only a table of different IP location services, but as well their relationship of interpreting geo feeds of IP resources, and whether or not they are following or adopting the RFCs that were published for geo feeds to accept said file formats, and their reactivity to geo feed updates. Here is an example of looking up a IP that is part of Netflix that can show that Netflix is publishing geo feeds themselves and has updated their route records accordingly to include this such that you can effectively see it when you look up their destinations. And here's an example of me just trying to find not only the Netflix geo feed, which is published, but in particular, a nearby destination to San Francisco. So the closest one I could see there is San Jose, and that's an example of a geo feed, nothing more, and how the standard effectively looks. Here is I think I have one more slide left. Second to last slide here is an example of querying MaxMind for 3 different destination IPs, one being the University of Davis cs.networks.ucdavis.edu, as well as a couple other destinations from Scenic and DePaul to understand how MaxMind in particular sees these destinations and effectively results in some sort of location. Different networks use these IP location services for different intents. MaxMind is just one of them, and this was a web tool that I could just show an example of their interpretation of where these IPs are located. Not trying to get into the politics at all of whether or not that who's authoritative for said location, or should location services be based off of IP or not. And last but not least, as been cited in different talks before, you can defer location somewhat through traceroute itself. Looking at this trace to this destination from Scenic, in the actual hops itself, we can call out some airport codes like LAX and make some other inferences like Fresno or Riverside from these trace outputs, in particular the DNS names correlated with these hops, and interpreting some form of location. I apologize the amount that I've stumbled over myself in this talk and have probably glossed over some very sensitive topics for some, but effectively that's all that I have. I did my best to do a high gloss summary, and if anybody has any questions, I'll take them now.
Hi, Quincy from Cloudflare. One thing that I thought you could mention is carrier neutral versus like incumbent ISP-owned interconnection facilities, which are like more common in some parts of the world than others. So your slides kind of focus on like, oh, hey, if you're at this IXP with this other peer that you want to peer with, you can 100% peer with them as long as like both parties want to do it. But in these non-neutral facilities, if the owner of the facility is like an incumbent ISP, they may have a vested interest in you not peering with that other provider, even though the two parties would want to peer. So that's happened to us a couple of times where like, hey, we want to peer with these guys, but the facility is like, no, we'll kick you out if you do that. So
Thanks for that feedback.
Hi, Sid, excellent talk, by the way. I love the overview, the broad overview of so many things. Question about Starlink class of satellite internet services and how it relates to the first part of your talk, which was the fixed internet, the exchange points and BGP routing. How do you think those new models of ISPs affect the rules and practices, and what are your views on those things?
Yeah, so I actually had in a previous draft reference to satellite services, but I just felt like it was getting into the minutia a bit. It is a growing point or form of interconnection. In the past, I think satellite services were often correlated with like rural communities that didn't have any other means of terrestrial connectivity. Nowadays, we are seeing a more abundant service being available at higher bits per second and reasonable latency that doesn't necessarily be noticed by the end user as much. So I think it is, in short, a different form of interconnection that's growing. There are different talks across the NANOG circuit that have talked about, in particular, these satellite services and how they're being used in different ways. I don't really have further comments in terms of like, I think, in terms of politics per se. But yeah, it is definitely a form of interconnection that I didn't mean to neglect, but I just don't think that today, at least, it is the vast majority of how people interconnect with the internet is my only point.
Hi there, Jack Kingsman, Atlassian. I don't have an ASN to play with. Are there any either interactive learning platforms or sandboxes or sort of a way to learn by doing with this that you particularly like or recommend?
Yeah, I mean, some of them I've kind of highlighted in this talk where, this is just effectively web tools that anybody can use in API endpoints without having any ASN. But maybe if you could be more specific with your question in terms of a sandbox.
So, fundamentals of routing an announcement, and I would like to, with the concept of, okay, I've got these ASNs and I want to do interconnection and I want to split a prefix and combine a prefix, and like something where you can kind of play with that in a simulation, basically.
Yeah, there are different lab environments that you can effectively emulate on machines such as GNS3, Container Lab, where you can effectively load network operating systems into these emulators. If not, Container Lab actually just like loading in Docker containers that you can build interconnection with, effectively configure these routers to do whatever you want in a virtual manner, and test against policy, which is actually very much so used actually in large networks of today for validating their changes before they actually go out to the production network itself. So not just in terms of exploring or learning, but it's actually very much so used today as a form of quality assurance. So I personally recommend Container Lab. It's what I've been using more so than ever, I would say, the last 5 years. And it's pretty easy to define configurations within Container Lab, boot up virtual routers, and play with them to your heart's desire of, in particular, there are ASNs reserved for research and labbing purposes. So like, for example, AS65535, and you can play around in this lab environment pretending to be AS65535, peering with different networks that you can peer on different or configure on different virtual routers and test routing announcements, policy, BGP convergence timing, etc. Even RPKI row validation, you can set up RPKI validators within Container Lab to have these virtual routers validate against to determine if routes are valid, invalid, or unknown.
Very cool. Thanks for a fantastic talk.
Thanks.
Hi. Sudhi, I'm with Meta. I was wondering, what is the adoption level of RPKI ROA, and will it be mandatory at some point for new ASNs coming online?
Yeah, sorry if I didn't clearly state that, but that's actually what these slides were meant to highlight, at least for IPv4. Didn't mean to neglect IPv6 here, but had a lot of content to go over. In particular for IPv4, we can see that out of all the IP space that is seen by NIST, 60% are covered by ROAs today. About 38% do not have any ROAs at all, and about 2% are invalid. So actually being routed, being seen with an RPKI ROA, still effectively being routed and seen by NIST, which, some are being done for research purposes. Others are actually invalid and should be filtered out, but effectively are still being seen. And this graph in particular can show a time series of, how RPKI adoption has progressed, at least for IPv4. NIST has the same for IPv6. I just didn't include it in these slides. And given that it's a newer protocol, I think that has something to do with it in terms of like Doug's call out there. So yeah, IPv4, there's just still a lot of work to be done in terms of RPKI ROA coverage. It's growing, and I think, in the beginning of 2024, if I'm reading that time series correctly, we kind of crossed the point there of, or not kind of, we did cross the point there of more valids than no RPKI ROA published at all.
Is it mandatory now for any new ASNs coming online to be compliant or to handle RPKI ROA?
Not that I know of.
If somebody comes to a cloud provider, like the AWS, if you're on address space, they're going to ask you to have a ROA. So that's not something legal, but there are some policy mandates that are forcing for adoption.
Yeah, so that's a great call out, and just to say it into the mic. So, the question was based off of like, if I'm actually going to go to an RIR and get my own ASN and IP space, am I required to publish a ROA or an ASPR record for anything? Today, not that I'm aware of by any RIR. They're all, having their own definitions of what to expect, but not to my knowledge. If you are actually to bring your own IP space to a cloud provider, as Doug mentioned, in particular, now there are even more constraints of not only they are not as much or willing to as they were before to route the IP space for you from their ASN, but in particular, you should route that IP space to them, originating from your own ASN, and then ideally as well having RPKI ROA records published to effectively facilitate them as your upstream.
Hey, Tony Tauber from Comcast. Just as a response to that, I think there's a talk later today, I believe at 2 on barriers to RPKI adoption. So I think that's
Oh, all right. Thank you.